In the summer of 1940, German ordnance engineers assembled in conference rooms across the Reich to review a decade of classified research into one of the most ambitious weapons concepts ever attempted. Their conclusion was unanimous and emphatic. An artillery shell that could detect a nearby aircraft, judge the distance, and detonate itself automatically was a physical impossibility. The acceleration forces involved in firing a cannon would shatter any electronic device known to science. The miniaturization required exceeded the boundaries of current engineering by an order of magnitude. After 10 years of sustained effort across more than 30 separate research programs, Germany officially abandoned the proximity fuse as a technological fantasy that no nation on Earth could achieve. At that same moment, 8,000 kilometers away, a 39-year-old American physicist named Merle Tuve was receiving a visitor from Britain who carried secrets in a small black metal box. Tuve had never designed a weapon in his life. He was a pure scientist who had spent his career bouncing radio waves off the upper atmosphere and smashing atoms in laboratory particle accelerators. He knew nothing about artillery ballistics, nothing about military procurement procedures, and nothing about industrial mass production techniques. But when Tuve heard what the British had attempted and where they had failed, he did not see an unsolvable problem. He saw a challenge that required the right combination of physics, engineering, and sheer determination. Within weeks, Tuve told his small team of researchers that they would develop a working proximity fuse and deliver it to the American fleet in combat quantities. They would accomplish this in less than 3 years. The Germans had tried for a full decade and concluded that the task was physically impossible. Merle Tuve was about to prove them catastrophically, decisively, and permanently wrong. The weapon his team created would help determine the outcome of the largest and deadliest war in human history. To understand why German engineers believed the proximity fuse was impossible, you must first understand the brutal physics of what happens when a naval gun fires. A standard 5-inch shell accelerates from a standing start to 2,600 feet per second inside a gun barrel approximately 15 feet long. This acceleration occurs in roughly 15 thousandths of a second. The mathematics are unforgiving. Every component inside that shell experiences a force 20,000 times greater than normal gravity. 20,000 Gs of crushing setback force, slamming every internal part backward with violence that defies ordinary human comprehension. Consider what this means in practical terms. If you weigh 150 pounds and experienced 20,000 Gs, the equivalent force on your body would be 3 million pounds. You would be compressed into a thin film instantly. Metal deforms under such stress. Glass shatters. Solder joints crack apart. Delicate wire filaments snap like threads. But the punishment does not end with linear acceleration. The rifling grooves cut into the gun barrel engage the rotating band on the shell and spin the projectile to stabilize its flight. By the time the shell exits the muzzle, it is rotating at approximately 200 revolutions per second. The centrifugal force generated by this rotation tears outward at every internal component, trying to rip parts away from the central spin axis. Now consider the electronics available in 1940. Vacuum tubes represented the only technology capable of amplifying electronic signals. These were glass bulbs containing thin wire filaments, metal electrodes, and trace amounts of gas or vacuum. They were notoriously fragile even when sitting motionless on laboratory benches. Radio operators in the field replaced burned-out tubes constantly. Researchers in universities handled them with extreme care to avoid cracking the glass envelopes or damaging the microscopic internal structures. The notion of building a complete radar system inside an artillery shell seemed utterly absurd. A functional proximity fuse would require a radio transmitter to send out detection signals, a receiver to capture reflections, amplification circuits to boost weak signals, a power supply to energize all these components, and a detonation trigger connected to the explosive charge. All of this hardware would have to fit in a cylindrical space smaller than an ice cream cone. And every component would have to survive being fired from a naval cannon that generated acceleration forces capable of crushing solid steel. A single miniature vacuum tube of the type that might be used in such a device weighed approximately 3 grams. Under normal conditions, 3 grams is negligible, roughly the weight of a penny. But at 20,000 Gs of acceleration, that 3-gram tube experiences the equivalent of 60 kilograms of crushing force. That equals roughly 130 pounds concentrated on a glass envelope smaller than your thumb. Ralph Baldwin, an American physicist who worked on the Fuze development program and later authored a definitive history of the effort, described this challenge in memorable terms. Imagine a full-grown woman standing with all her weight on a single stiletto heel, pressing down on a tiny glass tube. That was the load these delicate components had to survive. Not once, but thousands of times during manufacturing tests, and they had to survive while still functioning with timing precision measured in microseconds. German engineers understood these numbers with perfect clarity. They had performed these calculations repeatedly over 10 years of sustained research. They had attempted acoustic fuses designed to detect the sound of aircraft engines. They had developed electrostatic sensors meant to measure the electrical field surrounding metal aircraft bodies. They had experimented with photoelectric triggers designed to react to shadows, infrared detection systems, electromagnetic sensing arrays, and radio reflection systems fundamentally similar to what the Americans would eventually perfect. More than 30 distinct technical approaches were pursued across competing programs in the German Army, Navy, and Air Force. None achieved reliable performance suitable for mass production. The Rheinmetall-Borsig electrostatic fuse reached 95% reliability in controlled laboratory conditions. The program was halted in 1940 as resources shifted to other priorities, restarted in 1944 when desperation demanded new solutions, and terminated when Allied forces overran the production facilities. The Kranich acoustic fuse developed by Ruhrstahl AG and the Fuchs radio fuse built by AEG Berlin came closest to operational capability. Neither ever reached the front lines in functional form. By 1940, the official German position crystallized into certainty. Proximity fuses represented a technological dead end. Sophisticated nations should stop wasting precious wartime resources on a concept that violated fundamental engineering constraints. The physics simply did not allow such a device to exist. This conclusion rested on careful technical analysis performed by competent professionals, but it contained a fatal assumption that would prove catastrophic. German engineers measured what was possible by what had already been achieved in existing laboratories. They did not account for what might be accomplished by people operating under total war conditions who simply refused to accept that impossible actually meant impossible. The crisis that demanded a proximity fuse arose from brutal arithmetic that was killing sailors, soldiers, and civilians by the thousands every month. Anti-aircraft gunnery in the late 1930s was an exercise in mathematical frustration that bordered on futility. To destroy an enemy aircraft with an exploding artillery shell, gunners had to predict with near-perfect accuracy exactly where that fast-moving target would be located several seconds in the future. They had to calculate range to the target, bearing relative to their position, current altitude, airspeed in 3 dimensions, and rate of climb or descent. They then had to set mechanical timers on their shells to detonate at precisely the predicted intercept point in 3-dimensional space. The calculations were essentially impossible to perform perfectly under combat conditions. Aircraft maneuvered unpredictably, changing course, speed, and altitude without warning. Multiple targets often appeared simultaneously from different directions. Weather conditions, including wind, temperature, and barometric pressure, all affected shell trajectories in ways that were difficult to measure in real time. Even the best-trained gun crews using the most advanced fire control computers available missed their targets constantly. Analysis of actual combat engagements revealed the devastating truth. Approximately 2,000 anti-aircraft shells were required on average to shoot down a single enemy aircraft, 2,000 expensive rounds. 2,000 chances for gun crews to be killed by strafing runs while they frantically reloaded their weapons. 2,000 failures for every single success. Admiral Arleigh Burke, one of the most aggressive and highly decorated American naval commanders of the entire war, described this grim reality with characteristic bluntness. Mechanical time fuses only brought down aircraft at night by accident. They harassed enemy pilots and sometimes forced attackers to fly higher or approach from different angles, but they rarely actually killed anything. Britain grasped this existential problem with desperate clarity born of facing it directly. On October 30th, 1939, barely 8 weeks after Germany invaded Poland and ignited the Second World War, a British radar designer named William Butemont submitted a formal proposal to military authorities. He suggested two types of radio proximity fuse that might solve the anti-aircraft problem. One version would use ground-based radar to track shells in flight and transmit detonation commands at the optimal moment. The other design would be entirely self-contained, using the Doppler effect to detect nearby targets without any external assistance. The Doppler principle underlying the self-contained design was elegant in concept. A tiny radio transmitter built into the nose of a projectile would continuously broadcast a signal on a specific frequency. Most of this radiated energy would dissipate harmlessly into the surrounding air. But when the projectile approached a metal target such as an aircraft, some portion of the signal would reflect back toward the projectile. The reflected wave would be slightly shifted in frequency compared to the outgoing signal because of the relative motion between projectile and target. This is exactly the same principle that makes an approaching ambulance siren sound higher pitched than a receding one. An electronic circuit built into the fuse could detect this frequency shift between outgoing and returning signals. When the Doppler shift exceeded a predetermined threshold, indicating that the target was within lethal range of the shell's explosive charge, the circuit would automatically fire the detonator. No human calculation would be required. No mechanical timer setting. The shell itself would sense its target and autonomously choose its own optimal moment of detonation. British scientists at Cambridge University and the Pi Electronics Company worked intensively to translate this elegant concept into functioning hardware. Physicist John Cockcroft led coordinated efforts to develop vacuum tubes rugged enough to survive gun launch forces. Progress came with agonizing slowness. Rockets provided useful test platforms because they accelerated relatively gently compared to artillery and did not impose spin forces. Prototype fuses worked successfully when fired in rocket applications, but adapting the technology to survive artillery launch proved far more challenging. Britain, fighting desperately for national survival against German submarines, strangling supply lines and German bombers devastating cities, lacked the industrial capacity to pursue proximity fuse development at full scale. Every engineer, every factory, every ton of raw materials was already committed to producing Spitfire fighters, Lancaster bombers, tanks, and ships. There was no slack anywhere in the system for speculative weapons development that might or might not produce results. The solution to this resource constraint emerged in September 1940, when the legendary Tizard mission arrived in the United States. Sir Henry Tizard led a British scientific delegation carrying the most valuable military secrets in the entire British Empire. These secrets were offered freely to the Americans, a calculated gamble by Winston Churchill to cement American support before the United States formally entered the war. The black metal box that Tizard's delegation brought contained the cavity magnetron, a revolutionary radar component that historian James Finney Baxter later called the most valuable cargo ever brought to our shores. But the box contained other secrets as well. On September 19, 1940, at the Wardman Park Hotel in Washington, John Cockcroft personally disclosed the full details of British proximity fuse research to Merle Tuve. Tuve was already positioned to act immediately on this information. 3 months earlier, on June 12, 1940, an MIT-trained administrator named Vannevar Bush had met President Franklin Roosevelt with a single-page proposal for creating a National Defense Research Committee to mobilize American science for military purposes. Roosevelt read the brief document, asked a few clarifying questions, and approved the entire plan in under 15 minutes, writing simply "OK FDR" on the paper. On August 24, 1940, Tuve was officially appointed to lead Section T of this new research committee. The letter T stood for his own name. He established initial operations at the Carnegie Institution's Department of Terrestrial Magnetism in Washington, and immediately began recruiting the best available scientific talent from universities and industry across the country. Tuve was born in Canton, South Dakota, on June 27, 1901, the son of a college president and grandson of Norwegian immigrants. He earned his doctorate from Johns Hopkins University in 1926. In 1925, working in collaboration with Gregory Bright, Tuve had used pulsed radio waves to measure the height of the ionosphere, fundamental research that laid theoretical groundwork for the later development of radar. He had constructed particle accelerators and conducted pioneering nuclear physics experiments throughout the 1930s. Tuve combined deep theoretical knowledge of physics with practical experimental skill developed over decades of laboratory work. Most importantly, he possessed an absolute refusal to accept that any engineering problem was fundamentally unsolvable. His childhood friend and next-door neighbor growing up had been Ernest Lawrence, the physicist who invented the cyclotron and would later receive the Nobel Prize. He acknowledged throughout his later life that the British had provided crucial conceptual foundations for the proximity fuse. "We heard rumors of circuits they were using in rockets over in England," he explained to interviewers. "Then they gave us the circuits directly," but he was equally emphatic about what happened next. "The fuse design delivered by the Tizard mission was not the one we eventually made to work. The British had demonstrated that proximity fuses might be theoretically possible in low-stress applications like rockets. The Americans would prove the concept definitively by building more than 22 million artillery fuses that worked reliably under the most extreme conditions imaginable." Tuve established a laboratory culture unlike anything previously seen in American weapons development. He recruited Harry Diamond and Wilbur Hinman from the National Bureau of Standards to design the core Doppler detection circuits. Working with intense focus through December 1940 and the following months, they developed functional schematics that would prove essential to the program's success. Their radio frequency oscillator design became the beating heart of the proximity fuse, a transmitter and receiver system small enough to fit inside an artillery shell nose cone, yet sensitive enough to detect reflected signals from aircraft hundreds of feet away. On May 6, 1941, 6 experimental bomb fuses, built according to their design, were successfully tested at the Naval Proving Ground in Dahlgren, Virginia. The fuzes correctly detected approaching drone aircraft and triggered on command. This demonstration proved the fundamental concept could work under controlled conditions. But bombs represented the easy application. A bomb drops gently through the air under 1 g of gravitational acceleration, with no spin forces at all. The real engineering challenge was artillery shells, with their brutal 20,000 g setback forces and high spin rates. Solving this problem would require components that had never existed before. James Van Allen, a young physicist destined to later discover the radiation belts surrounding Earth that now bear his name, led the critical effort to develop rugged, miniaturized vacuum tubes capable of surviving artillery launch. His testing methods combined scientific rigor with brutal practicality. Researchers mounted prototype tubes in solid metal blocks and fired .22 caliber bullets directly at them. They sealed tubes inside lead containers and dropped them repeatedly from rooftops. They constructed compressed air cannons to fire electronic components at high velocity into sand traps, measuring which designs survived impact and which shattered. The testing regime was relentless and unforgiving. Tubes that survived 1 round of acceleration tests were immediately subjected to different stress patterns. Components were heated and frozen, vibrated and spun, dropped and fired again. Researchers kept meticulous records of every failure mode, analyzing cracked glass, broken filaments, and shattered electrodes to understand exactly which physical forces caused destruction. Each failure taught lessons that informed the next round of design improvements. Van Allen worked simultaneously with 5 different tube manufacturing companies, pushing each firm to experiment with stronger glass formulations, different internal electrode geometries, new filament winding techniques, and shock-resistant mounting systems. The fundamental problem was that conventional vacuum tubes relied on thin wire filaments suspended by delicate supports inside glass envelopes. Any of these elements could fail catastrophically under the violence of gun launch. Sylvania Electric Products eventually achieved the critical breakthrough, developing miniature tubes that weighed just 3 grams, yet survived 20,000 Gs of acceleration, reliably enough for mass production. The secret lay in using ceramic supports, stronger glass compositions, and electrode structures specifically designed to resist both linear shock and rotational forces. The power supply presented another seemingly impossible engineering challenge. Conventional batteries of the 1940s were far too large, heavy, and fragile to fit inside an artillery shell, while leaving room for all the other required components. In February 1942, engineers at National Carbon Company invented an elegant solution called the reserve wet cell battery. In this revolutionary design, the electrolyte fluid that enables a battery to generate electrical current was sealed inside a small glass ampule within the battery casing. The electrodes stood ready but remained completely dry and chemically inert until the moment of firing. When the shell launched, the massive shock of acceleration shattered the glass ampule. Centrifugal force from the spinning projectile then distributed the released electrolyte fluid across stacked plates of carbon and zinc. Chemical reaction began instantly, and electrical current flowed. This design served double duty as an essential safety mechanism. The fuse literally could not arm or activate until actually fired from a gun because the battery electrolyte remained physically separated from the electrodes during handling, storage, and transportation. Accidental detonations during ammunition supply operations became virtually impossible. Shells could be dropped, jostled during transport, and stored for extended periods without any risk of premature activation. Tuve posted handwritten dictates on laboratory walls that became legendary among the hundreds of people who worked under his direction. "I don't want any damn fool in this laboratory to save money," one proclamation declared. "I only want him to save time." Another stated bluntly, "The best job in the world is a total failure if it is too late." He instructed his team to shoot for 80% solutions because perfection was unaffordable under wartime conditions. "In a war, a D is necessary and enough," he told researchers. "An F is fatal." As Section T rapidly outgrew its original facilities at the Carnegie Institution, Tuve conceived and organized an entirely new research institution. On March 10, 1942, a formal contract between the Office of Scientific Research and Development and Johns Hopkins University established the Applied Physics Laboratory, which would become one of the most important defense research organizations in American history. Initial operations began in a converted automobile garage at 8621 Georgia Avenue in Silver Spring, Maryland. The staff expanded rapidly from approximately 100 researchers to more than 800 as the program accelerated toward production. The decisive proof of concept came on August 12, 1942 in the waters of Chesapeake Bay. The cruiser, USS Cleveland, conducted live-fire tests against radio-controlled drone aircraft flying realistic attack profiles. The Navy had officially scheduled 2 full days of testing, with multiple drones available as targets. They ended up needing only a single morning. 3 target drones were launched sequentially. 4 bursts of proximity-fused ammunition were fired. All 3 drones were destroyed. The Navy cancelled the entire remainder of the scheduled test program because no target aircraft remained and no further demonstration was necessary. Mass production orders went out to manufacturers immediately. The industrial mobilization that followed matched the scientific achievement in ambition, scope, and ultimate success. The proximity fuse program eventually involved 87 separate manufacturing firms operating 110 factories spread across the continental United States. More than 2,000 suppliers and sub-suppliers provided raw materials, precision components, specialized tooling, and support services. Each completed proximity fuse contained approximately 130 separate miniaturized parts, including 5 vacuum tubes, numerous resistors and capacitors, multiple amplifier circuits, the revolutionary reserve wet cell battery, a thyrotron trigger switch, and an antenna system cleverly integrated into the projectile nose cone. Crosley Corporation in Cincinnati became the first manufacturer to deliver accepted production fuses in September 1942. At peak output, Crosley employed 10,000 workers producing 16,500 fuses every 24 hours across 3 continuous shifts. Assembly lines never stopped. By the time Germany and Japan surrendered, Crosley alone had manufactured 5,205,913 individual fuses, representing roughly 24% of total American production. Sylvania Electric Products made perhaps the single most critical contribution to the entire program. 10,000 Sylvania workers, predominantly women recruited from local communities who had no prior electronics experience, produced 1 million miniature vacuum tubes every 2.5 days. This single company manufactured vacuum tubes at 2/3 the production rate of the entire American radio industry before the war began. Sylvania ultimately produced 95% of all vacuum tubes used in proximity fuses. The Sylvania assembly facility in Ipswich, Massachusetts, achieved particularly remarkable results. This single plant produced 5,683,032 completed proximity fuses during the war, the highest output of any individual factory in the entire program. Local women who had previously worked as housewives, store clerks, and factory hands in other industries learned to assemble electronic components with precision that matched or exceeded professional electrical engineers. The cost reduction trajectory demonstrated the remarkable power of manufacturing process optimization under wartime pressure. In 1942, when production first began, each individual proximity fuse cost $732 to manufacture. By 1945, through relentless process improvement and production line refinement, the cost had dropped to just $18 per unit, a reduction exceeding 97% achieved in roughly 3 years. Daily production capacity increased in parallel with falling costs. Output rose from 500 completed fuses per day in late 1942 to 40,000 per day, in late 1943 to 70,000 per day, during the war's final months. Total wartime production exceeded 22 million individual proximity fuses at a total program cost of approximately $1 billion. Not every fuse worked perfectly. Testing and combat experience revealed an approximate 30% dud rate, meaning roughly 3 out of every 10 fuses failed to detonate as intended. This might seem like a devastating reliability problem, but the mathematics still overwhelmingly favored proximity fuses over conventional time fuses, even accounting for the dud rate. VT fuses remained several times more effective than mechanical alternatives, because the 70% that did function properly detonated at precisely the optimal distance from targets, rather than at random points in empty sky. Women formed the backbone of this extraordinary manufacturing workforce. The delicate assembly of miniaturized electronic components required manual dexterity that the machines available in the 1940s simply could not match. Workers with absolutely no prior experience in electronics learned to solder connections smaller than matchstick heads and handle components barely visible to the naked eye. The secrecy surrounding the proximity fuse program matched the Manhattan Project atomic bomb effort in scope and intensity. The official designation VT, standing for variable time, was specifically chosen by Captain S. R. Shoemaker of the Bureau of Ordnance to mislead anyone who might encounter the term in classified communications. The name implied merely an adjustable mechanical timer rather than a revolutionary electronic sensing device. Workers in manufacturing plants were told they were building radio components. Most had no idea their work had any connection to artillery ammunition whatsoever. Security concerns intensified dramatically in July 1943 when American forces invaded Sicily. The landings at Gela on July 11th marked one of the first major amphibious operations where VT-fused naval gunfire supported troops ashore. Military planners worried constantly that unexploded shells containing intact fuses might be recovered from beaches or shallow water by German forces and shipped back to laboratories in the Reich for analysis. Every dud represented a potential security breach that could compromise the entire program. The Joint Chiefs of Staff imposed a remarkable and unprecedented operational restriction on proximity fuse deployment. VT fuses could only be used in combat over deep ocean water where any unexploded duds would sink unrecoverable to the sea floor. Use over land was absolutely prohibited, until the desperate circumstances of December 1944 finally forced a change in policy. The fear driving this restriction was that even a single intact fuse recovered by German or Japanese forces could reveal the secret technology and enable development of countermeasures or copies. Commander William Parsons, who would later achieve very different fame by arming the atomic bomb aboard the Enola Gay during the flight to Hiroshima, personally escorted the first shipment of 5,000 proximity-fused shells from the United States to the Pacific Fleet in late 1942. First blood came on January 5, 1943, in the waters near Guadalcanal. 4 Japanese HED-3A dive bombers attacked an American cruiser-destroyer task force returning from a bombardment mission against Japanese positions at Munda. Lieutenant Red Cochran, commanding the aftergun battery on the light cruiser USS Helena, opened fire on the departing enemy aircraft using VT-fused ammunition. 2 salvos. 1 Japanese bomber burst into flames and crashed into the sea. No direct hit had actually struck the aircraft. The proximity fuse had detonated one of the shells close enough to the target that expanding shrapnel shredded the aircraft in mid-air. Parsons documented this historic moment for official Navy records. On the 5th of January 1943, 4 dive bombers attacked the task force, one streaked by the cruiser USS Helena. 2 rounds were fired, and the first victim of the proximity fuse burst into flames and crashed into the sea. The combat statistics that accumulated over subsequent months demonstrated a complete transformation of naval anti-aircraft warfare. In 1943, proximity-fused shells constituted only approximately 25% of total anti-aircraft ammunition expended by American naval forces. Yet, this 25% of ammunition accounted for fully 50% of all confirmed enemy aircraft kills. VT fuses proved approximately 300% more effective than conventional time-fused ammunition. By 1945, as production increased and deployment expanded throughout the fleet, the effectiveness advantage had grown to approximately 600%. The physics of fragmentation patterns explained this dramatic improvement clearly. A conventional shell detonated by a mechanical time fuse exploded wherever its preset timer happened to expire, scattering shrapnel randomly in all directions through 3-dimensional space. Most of this lethal fragmentation flew harmlessly through empty air where no target existed. The effective lethal zone where an aircraft would actually suffer fatal damage measured approximately 60 square feet. A proximity-fused shell detonated at precisely the optimal distance from the target. The shrapnel pattern concentrated toward the aircraft, rather than dispersing randomly through empty sky. The effective lethal zone expanded to approximately 3,000 square feet, a 50-fold increase in lethality per shell. The weapon proved especially devastating against Japanese kamikaze attacks that began in late 1944. When conventional bombing and torpedo runs became essentially suicidal against American air defenses, Japanese commanders converted to deliberate suicide attack tactics as the only remaining option. But proximity fuses defeated even determined kamikaze attacks. 5-inch guns equipped with VT ammunition could reliably destroy incoming suicide aircraft at ranges where even a badly damaged and burning kamikaze could not complete its final dive into the ship. The attacking aircraft simply disintegrated before reaching its target. Off Okinawa on May 11, 1945, the destroyers USS Evans and USS Hadley formed part of a radar picket line, positioned to provide early warning of Japanese air attacks. They faced more than 150 kamikaze aircraft attacking in concentrated waves over several hours. Using proximity-fused ammunition, the 2 destroyers and their supporting vessels shot down virtually every attacking aircraft. A combat report filed afterward noted that the horizon from east to northwest was full of burning planes. The kamikazes fell from the sky faster than they could close the range to their targets. Naval historians subsequently concluded that the proximity fuse, combined with radar-directed fire control systems, eventually made conventional air attacks against American carrier task forces essentially impossible. This judgment helps explain Japan's increasingly desperate embrace of suicide tactics as the war progressed. When normal attack became demonstrably futile, suicide seemed like the only remaining option. The fuse proved equally decisive against Germany's V-1 flying bombs. When these pilotless terror weapons began devastating London in June 1944, killing thousands of civilians and threatening British morale, proximity fuses were rushed to anti-aircraft batteries positioned along the English Channel coast. The gun positions were deliberately located so any dud shells would fall into the sea rather than onto French territory where German forces might recover them. In the first week of the V-1 campaign, before proximity fuzes were deployed, conventional anti-aircraft fire using mechanical time fuzes destroyed only 17% of buzz bombs engaged. By late August, after proximity fuses were fully deployed throughout the defensive belt, the kill rate had risen to 74%. On the single most successful day of the campaign, 82% of V-1 flying bombs entering the defended zone were shot down before reaching London. General Frederick Pyle, commanding all British anti-aircraft forces, declared afterward that the proximity fuse made this dramatic improvement possible. General Dwight Eisenhower later reflected on what might have happened if Germany had deployed its vengeance weapons earlier in the war. It seemed likely, he wrote in his memoir Crusade in Europe, that if the German had succeeded in perfecting and using these new weapons 6 months earlier than he did, our invasion of Europe would have proved exceedingly difficult, perhaps impossible. But the most dramatic and strategically significant demonstration of proximity fuse effectiveness came during the Battle of the Bulge in December 1944. On December 16, 1944, approximately 200,000 German soldiers crashed through thinly held American lines in the Ardennes forest region of Belgium and Luxembourg. The offensive aimed to split Allied armies, capture the vital port of Antwerp, and force a negotiated peace before Germany faced total defeat. Tactical surprise was complete. American units found themselves suddenly surrounded, cut off from reinforcement, and fighting desperately in bitter winter conditions against an enemy that seemed to materialize from the frozen mists. On the morning the offensive began, Colonel Axelson of the 406th Field Artillery Group made a decision that technically exceeded his authority. Facing a tactical emergency of the highest magnitude, he deliberately broke the standing prohibition on using proximity fuses over land. The desperate situation, he judged, trumped security regulations designed for less critical circumstances. Within days, General Dwight Eisenhower formally requested official clearance from Washington to lift all restrictions. On December 19th, Eisenhower sent the request. By December 21st, all limitations on land use of proximity fuses were completely removed. 200,000 posit shells, the Army's code designation for proximity fused artillery ammunition, were unleashed against German forces attempting to break through American defenses. The effect on German ground troops was physically devastating and psychologically shattering beyond anything conventional artillery had ever achieved. Proximity fuses detonated incoming shells 20 to 50 feet above ground level, showering lethal shrapnel downward over wide areas with no warning and no possibility of escape. Foxholes and trenches, the traditional refuge of infantry under artillery bombardment, offered absolutely no protection against shells exploding directly overhead. Soldiers who had survived hundreds of conventional barrages found themselves completely vulnerable to this new terror from above. In the dense forests of the Ardennes, proximity-fused shell bursts combined with splintered tree branches and trunks to create horizontal storms of lethal debris that killed soldiers hiding behind trees. German prisoners captured after posit bombardments described the American artillery attacks as quick, powerful bursts against which there was simply no defense. Intelligence reports gathered from prisoner interrogations indicated that proximity-fused artillery caused something approaching mutiny in certain German units, with soldiers flatly refusing direct orders to leave bunkers and advance during American barrages. General George Patton wrote directly to the Chief of Army Ordnance with his characteristic bluntness and absence of diplomatic qualification. "The new shell with the funny fuse is devastating. We caught a German battalion which was trying to get across the Sauer River with a battalion concentration and killed by actual count 702. Patton's verdict on the weapon's importance became famous. "The funny fuse," he declared, "won the Battle of the Bulge for us." The deepest and most bitter irony of this entire story is that Germany had pursued proximity fuse development for a full decade longer than the Americans, possessed technical expertise fully equal to anything available in the United States, and actually captured 20,000 functioning proximity fuzzes during the Bulge. Yet German forces failed completely and utterly to understand or utilize what they had seized. When German soldiers overran an American ammunition supply dump in the Ardennes during their initial advance, they captured thousands of intact artillery shells equipped with functioning proximity fuses. German ordnance specialists subsequently examined these captured rounds in detail. They conducted tests, they analyzed components, they disassembled fuses, and documented what they found. They filed technical reports through proper military channels. They never grasped what they were actually looking at. Having concluded years earlier through their own research programs that proximity fuses were physically impossible to construct, German engineers simply could not recognize a working fuse when they held one in their hands and took it apart piece by piece. The captured American shells went completely unused. Their revolutionary principles remained uncomprehended. German commanders even issued official orders, offering rewards to frontline soldiers who could locate and recover intact fuses from the ground, after the mysterious American airbursts that were decimating their troops with unprecedented cues. Efficiency. These commanders never realized that they already possessed 20,000 perfect examples of the weapon sitting in captured supply dumps behind their own lines. The nation that had declared proximity fuses beyond the technical capability of any country on Earth was systematically destroyed by a weapon its own engineers could not recognize, even while holding functioning examples in their hands and disassembling them on laboratory workbenches. The scientists, engineers, and factory workers who accomplished this remarkable technological achievement did not become famous figures in the public consciousness after the war ended. Merle Tuve returned to pure scientific research at the Carnegie Institution when peace came. He studied cosmic rays reaching Earth from deep space, pioneered techniques of radio astronomy, and investigated the large-scale structure of the universe. He received the Presidential Medal for Merit, the highest civilian honor the United States could bestow. The British government named him an honorary commander of the Order of the British Empire in 1948 in recognition of his contribution to defeating the V1 menace. He died on May 20, 1982, celebrated by fellow scientists and defense researchers, but largely unknown to the broader American public, whose survival his work had helped ensure. Vannevar Bush became an elder statesman of American science policy in the post-war decades. His 1945 essay, titled As We May Think, published in the Atlantic Monthly, anticipated key features of personal computers and hypertext linking decades before such technologies existed. He remains among the most important figures in 20th-century American scientific administration, yet few ordinary citizens today would recognize his name. James Van Allen achieved lasting public fame, but not for his work on proximity fuses. His 1958 discovery of radiation belts surrounding Earth via Explorer appears in every physics textbook under his name. The miniaturization techniques he had developed for building electronics that survived artillery launch proved equally valuable when applied to instruments small and rugged enough to ride rockets into orbit aboard America's first satellites. William Parsons, who had championed the artillery shell Fuze throughout its development and personally escorted the first combat shipment to the Pacific Fleet, became part of an entirely different historical narrative. He served as weaponeer aboard the B-29 Enola Gay on August 6, 1945, responsible for arming the atomic bomb during the flight to Hiroshima. He died on December 5, 1953. The Applied Physics Laboratory at Johns Hopkins University did not disband as originally expected when the war emergency passed. Instead, it became a permanent institution, evolving into the foundation of American guided missile development for the following 8 decades. The Bumblebee program at APL achieved the first ramjet-powered test flight in June 1945. Laboratory engineers developed the Terrier, Tartar, and Talos ship defense missile systems throughout the late 1940s and into the 1950s and 60s. These systems evolved over subsequent decades into the Standard Missile family that continues protecting American naval vessels today. When the Soviet Union launched Sputnik into orbit in October 1957, 2 APL physicists named William Geer and George Weifenbach noticed the Doppler frequency shift in the satellite's radio transmissions and realized this phenomenon could enable precise satellite-based navigation. Their insight led directly to the transit navigation system used by Polaris missile submarines and eventually to the global positioning system used by billions of people worldwide today. The Applied Physics Laboratory currently employs more than 8,000 personnel. Secretary of the Navy James Forrestal assessed the proximity fuse's strategic importance shortly after the war concluded. The proximity fuse has helped blaze the trail to Japan. Without the protection this ingenious device has given the surface ships of the fleet, our westward advance could not have been so swift, and the cost in men and ships would have been immeasurably greater. Admiral Lewis Strauss placed the proximity fuse in proper historical perspective alongside other decisive technologies. While no one invention won the war, the proximity fuse must be listed among the very small group of developments, such as radar, upon which victory very largely depended. What ultimately explains the difference between German failure after a decade of effort and American success achieved in less than 3 years. The German misjudgment was not a failure of intelligence or technical education. German engineers were brilliant and rigorously trained. They understood physics and mathematics as well as any researchers alive. They had adequate financial resources, talented personnel, sophisticated laboratories, and a 10-year head start. Their failure was organizational and psychological rather than purely technical. They scattered limited resources across dozens of competing programs run by rival military services, that refused to share information or coordinate their efforts. They measured what was possible by examining what had already been achieved in existing laboratories, rather than imagining what might be accomplished under conditions of total national mobilization. They allowed reasonable assumptions to harden into unexamined certainties that prevented them from recognizing solutions, even when those solutions were literally placed in their hands. The Americans who succeeded possessed no inherently superior scientific knowledge. They had no better raw materials. They commanded no magical advantages unavailable elsewhere. What they possessed was unified organizational structure under Tuve's demanding leadership. They possessed manufacturing capacity mobilized with total wartime urgency by companies that had never built electronic devices before. Most importantly, they possessed a categorical refusal to accept that expert consensus about physical impossibility represented actual physical law that could not be overcome through determined effort. American researchers recruited factory workers who had never touched an electronic component and trained those workers to assemble circuits measured in fractions of millimeters with their bare hands. They developed vacuum tubes that survived forces 20,000 times normal gravity through relentless iteration, building and testing thousands of experimental designs until configurations emerged that survived. They invented batteries that armed themselves automatically when fired from cannons by shattering their own internal components. They mass-produced 22 million precision electronic devices, while simultaneously reducing unit manufacturing costs by 97%. The shells that could think, the weapons that sensed their targets and autonomously selected their own optimal moments of detonation, emerged not from superior intellect, but from superior organizational will, applied through superior manufacturing coordination. Nations still underestimate adversaries based on observing peacetime performance rather than wartime potential. Experts still declare technologies impossible based on examining current laboratory limitations rather than imagining future capabilities. The strategic cost of such misjudgment remains as severe today as it was 8 decades ago. If you found this story compelling, please take a moment to like this video. Your engagement helps us share more forgotten history from the Second World War with viewers who care about preserving these stories. Subscribe to stay connected with future episodes covering topics that deserve to be remembered. Leave a comment telling us where you are watching from today. Thank you for watching, and thank you for helping keep these stories alive.